Diffraction begins when the wind blows over the ocean's surface. The wind friction stretches the water surface, which forms small ripples, which are called capillary waves. The capillary waves deflect the surface wind upward, slowing it and causing some of the wind's energy to be transferred into the water to drive the capillary wave crest forward. Once formed, wind waves travel in groups which are called wave trains. When the wavelength exceeds 1.74 centimeters, the capillary wave becomes a gravity wave, and as the steepness of the wave increases to a 1:7 ratio and a 120-degree angle, the top is blown off and forms a white cap. Wave size increases with wind speed, duration, and fetch. As waves approach the shore, they are subject to a number of processes, including wave shoaling, refraction, and diffraction.
Wave shoaling. Wave shoaling is the effect of surface waves entering shallower water, resulting in an increase of wave height and decrease of both wave speed and wavelength. Wave shoaling occurs in water depths less than half of a wave's length. Eventually, the surface waves that go through this process turn into surf. Shoaling happens because waves experience force from the seabed as the water gets shallower.
So, what happens when a water wave moves across an area of differing water depth? The answer is refraction. Wave refraction is the process where water waves bend due to differing celerity. Wave celerity increases with depth. This means that in shallow water, waves travel more slowly than in deep water. Here we have a wave crest approaching the coastline in a relatively straight line. As the middle of the wave crest approaches shallow water around the headland, it interacts with the sea floor and reduces its celerity. The outside section of the wave crest continue to travel at a greater celerity, and this causes waves to bend inwards towards the headland. As a result, waves converge and energy becomes concentrated at headlands.
Surfing is the only life, the only way for me now. Surf, surf.
So, what's so cool about refraction causing wave energy to concentrate at headlands? 50-foot waves pounding into the headlands of Pillar Point, California. That's what. The unique bathymetry extending about a mile of Pillar Point causes wave refraction to occur, and as a result the surf can reach over 50 feet high. This extremely powerful surf break, known as Mavericks, has deep channels on either side that create refraction. The refraction causes waves to bend towards a shallow ridge, and this focuses the wave energy. Another process which waves are subject to is diffraction. When moving through an aperture, diffraction causes wave energy to propagate along the crest. This causes the wave to spread out. So what controls diffraction? Diffraction is controlled by the different sizes of aperture. The narrower the aperture, the more diffraction that occurs. The wider the aperture, the less diffraction that occurs. Diffraction is also controlled by the order of the wavelength. If the aperture is smaller than the wavelength, then a more circular front will form and more diffraction occurs. If the aperture is larger than the wavelength, then less diffraction occurs.
Now we come to the end of a wave's journey, where water comes in contact with land. As a wave reaches shore, the wave slows down due to friction. As the wave slows down, its height increases until it reaches a critical point and then collapses. When this happens, the wave is termed a breaking wave. There are three major types of breaking waves, and how they break is determined by their speed as they approach the shore and the angle or steepness of the shore. A gentle beach slope produces a spilling breaker. The wave speed does not drastically reduce as the wave strikes the beach, resulting in the top and bottom of the wave travelling at much the same speed. The top of the wave just slides down the front of the wave. A moderately steep beach slope results in a plunging breaker, the most common breaking wave for surfers. Here, the top of the wave travels faster than the base of the wave, due to the base of the wave slowing down on the beach slope. The resulting wave takes a tunnel form as the top falls over due to its height being too tall. The steep beach slope causes the wave to decelerate quickly. The wave appears as if they are breaking backwards, as the bottom of the wave surges forward. This waveform is called a surging breaker, and it is dangerous due to its strong undertow.